Hello everyone, and thank you for attending our talk on HPE iLO5 security. So first let's introduce ourselves. So with me Alexandre Gazet, who is a security engineer in Airbus Security Lab. He's also the co-author of the practical reverse engineering book. And I'm Fabien Périgaud. I'm the reverse engineering team technical lead at Synactive. I'm also a vulnerability researcher and a CTF and security challenge enthusiast. Our third partner in crime, Joffrey Czarny, couldn't attend the recording of this video. So let's talk about iLO. So iLO is a full system running on a dedicated hardware in every HPE servers in the world. So it allows system administrators to be able to perform various administrative tasks on the server as if they were physically close to them. So for example, they can recover various information such as the temperature graph you can see on the image, but also have all the features of an IP KVM, such as rebooting the server to boot on another media, etc. So iLO is a technology we already know. We did a deep dive analysis of HPE iLO4 and iLO5 back in 2018. So we found various vulnerabilities such as a pre-authentication RCE on iLO4 to full secure boot bypass on iLO5. And we also abused the DMA feature to be able to compromise the host operating system by executing code on iLO. So how did this new study started? Back in early 2020, new iLO5 firmware versions appeared, versions 2.x. When we downloaded these new firmware versions, we thought that they were in fact high entropy data blobs, so it seems that these new updates were encrypted. While looking at the installation notes, we saw that to be able to upgrade to these new versions, we first had to install iLO5 version 1.4x. So it seems that these firmware versions were transitional versions, and fortunately they are unencrypted, so we could start studying them to understand the new format.
Okay, so right now our objective is to understand where the firmware are decrypted by the iLO system. And of course, we want to hopefully re-implement that mechanism and update our firmware analysis toolbox. Our first guess was that the decryption will be implemented quite early in the boot process of the iLO5 systems, possibly in one of the first two bootloaders, Secure Microboot or NEBA 9, or possibly within the kernel. However, if we compared versions from firmware 1.3x and version 1.4x, the versions were actually exactly the same. There was no change, so the decryption mechanism is not implemented during that stage of the boot stages. The next hypothesis we made was that it could be in the userland image, and more specifically in one of the userland tasks that we know very well, which is the Firmware Update Manager, or FUME. This task is responsible to verify the cryptographic signature of the new firmware update file, and if the check is successful, to write that firmware update within the SPI flash memory. And indeed, if we diff quickly two versions of this userland task, we discovered the decryption mechanism. So to give you a quick overview, what is used is called envelope encryption. It relies upon OpenSSL primitives, and an authenticated symmetric ciphering of the data is used. An algorithm is AES in Galois counter mode, or GCM. And the symmetric key of the AES algorithm is actually sealed by an asymmetric encryption algorithm, and RSA is used. If you want to open the envelope or unseal the symmetric key, you have to use and access the RSA private key. So now we are looking for this private key. We quickly located this private key in the data, in the resource of the userland task. It is in format PKCS8, and the RSA private key is protected by a passphrase. Again, the code relies upon OpenSSL primitive, and in this time, more specifically, PM read BO RSA private key. And actually, there is a callback function that feeds the passphrase to this OpenSSL primitive. So if we pursue our analysis and we look at how this callback function is implemented, we have named it PM password CB. What we observe is that the buffer we name HW secret is actually built from very specific memory ranges that we knew from our previous research on the topics, and these memory ranges actually are configuration registers from the iLO5 system on chip, the processor itself. So kind of hardware registers mapped into the virtual memory of the userland task. So that means that the HW secret buffer is actually kind of a hardware key. So we have an understanding of the global picture here. Our objective is to gain access to the iLO5 system to read these SOC registers and hopefully extract the key. The simplest way to do that is to exploit a vulnerability on the iLO5 system. At this step, we were very pragmatic. We reused an exploit released and a vulnerability released in 2018 by Nikolaios. It impacted iLO 4 and 5. It is a remote execution of arbitrary code in the proprietary SSH restricted shell. The vulnerability is a type of type format string, and Nicola released exploitation code for iLO 4. So what we did was to port the first stage of this exploit to iLO 5. In order to do so, we encounter a couple of difficulties. The first one is that the vulnerability is located within the task con app CLI, which is the implementation of the restricted shell. And within this task, the SOC secret, the SOC registers are not mapped. The second difficulty is that with the format string vulnerability, we obtain a read-write memory primitive. However, there are some constraints. First of all, addresses with null byte are forbidden, as well as some special characters in the addresses again, like \n or \r. To bypass these difficulties, we had to implement a couple of tricks. So to solve the first issue, we used a hook of a function pointer in the memory of the user on task to actually call a primitive exposed by the operating system that is quite close to a mmap function. I will come back on it just after. For the second difficulty, we use a kind of double mapping trick to remove null bytes from addresses. So, back to the mmap equivalent function. So it is kind of on request memory mapping. It is the function we have named it memmap. It is a high-level wrapper upon kernel primitives. But what is very interesting is that the behavior of this function depends upon structures that are defined within the userland task, in the memory of the userland task. And more specifically, if you look at the top left of the slide, you can observe that the structures are defined in a readable and writable memory area of the userland task. So each one of these structures is really simple. It's kind of a mapping descriptor. We guess that it describes some devices that can be mapped within the userland task. For example, it's not possible to directly map the full memory of the kernel in a userland task. It would have been too simple. So each structure is a kind of a mapping between a physical memory and virtual memory, and we also have what we have called a mask that is used to tell to the API which memory range you want to map into memory. And yes, these structures are defined in a readable and writable memory of the task. So, as you can guess, we have abused this fact. For example, we have patched one of the descriptors to make sure that one physical memory which was of specific interest for us, because that's where the hardware registers are mapped. We have used this descriptor to map it at another virtual memory, virtual addresses, where actually to remove the null bytes from the addresses. So it solved one of our difficulties. So at the end, we actually quickly managed to extract the key from the iLO5, from the memory of the iLO5 system, performing the key extraction using a format string over the VPN, over a VPN, because our servers were located elsewhere. And very quickly, we were successfully decrypting the firmware.2x. So, what do we have new in this firmware in version 2.x? Sorry. What is really new is that now we have 3 userland images. There used to be only 2, a main image where all the iLO firmware will be located, and a recovery image only. Now we have 3 images, like I said. What we observe is that there is a new kind of image, and it is very, very small. It is actually even smaller than the recovery image. And what is really important is what used to be the main image, the biggest one, I would say. Now it is again encrypted. So we have a new images, very small, that is not encrypted, and that will be our lead to understand what happened. And that's exactly the feeling we had at that time, that the princess was indeed in another castle. So quite quickly we come to the conclusion that there is a second encryption layer, and again our objective will be to extract the encryption key and hopefully re-implement all the stuff in our firmware analysis toolbox. So if we dissect a little the new very small userland image that we find in the new firmware, we observe that it is it only embeds 3 shared modules, 3 libraries. The first one is lim integrity, so So basically the interface with the operating system. We have the libc and libopenssl, so you can guess, we will have cryptography involved. If we look at the list of tasks, this image is a single task image. So the only task that run is named key manager, key or key mgr, and we will name this image key mgr as well. So to give you again an overview of what is at stake here, actually we have a kind of an augmented boot chain. Instead of the kernel jumps directly to the main images, we have now what we have called a stager, that is key manager. And key manager is responsible for loading and decrypting in memory the new secure main image. And I use the word secure because it is encrypted. Okay, so now we want to extract the key from the key manager. We are looking for the key maker. So the new main userland image are encrypted. The same envelope encryption mechanism is used. However, instead of using RSA for the asymmetric part, some cryptography over elliptic curve is used. What happens is that when key manager starts very early in its boot, a private key is reconstructed. This private key is combined with some public part located in the header of the new encrypted userland image. And basically what is used is a Diffie-Hellman algorithm over the elliptic curve to derive a shared secret, and this shared secret is later used to derive the AES encryption key, the symmetric encryption key used for the AES in GCM mode. So the reverse engineering of key manager was already a great challenge, especially because we had a new unknown factor, a new X factor that was totally unknown to us at the beginning of this study, which is a hardware cryptoprocessor. Regarding this cryptoprocessor, this hardware element, we had absolutely no specification, no developer documentation or anything. So we were really kind of blind at the beginning. Quickly we realized that only 3 operations were used from this cryptoprocessor. The first one is a SHA-384 primitive, and we have an AES in counter mode and another AES in Galois counter mode, so authenticated mode. The private key is reconstructed regularly in the boot of key manager. There are 2 main steps. The first one is the derivation of a seed from hardware values. So on the top left of the schematic, and on the top right we have the key scheduling function that is fed by the seed that is derived first. So if we go back on the derivation of a seed, there are actually 2 inputs value. The first one that we name boot hash is actually, we understand that thanks to our knowledge of the system, actually it is an artifact of the verification of the signature of the first bootloader by the boot ROM of located on the processor itself. So we have kind of residual context that stays on the output buffer of the cryptoprocessor, and it is used as input value for the derivation of the initial seed. The second input that we name hardware key is actually a buffer made from, again, hardware registers from the iLO5 SOC. So you combine boot hash and hardware key using a derivation steps based on SHA-384, and you got the derivation seed. This derivation seed is then proceeded to the key scheduling function. The key scheduling is kind of really complex. So we will not enter into every details here, but you can find all the information in the paper that we published on the GitHub of the project as well. Today we will just speak about two key elements, I will say. The first one is what we have called commands. They are like wrapper over the cryptoprocessor, kind of derivation steps based again on the SHA-384 primitive. And this derivation step is parameterized by a key. You have commands like key schedule, derive kx, or drgb seed lb. The second very important point is how do you generate a deterministic key? Because key manager use OpenSSL primitive like EC key generate key, and if you use that in your code on your machine, it will generate for you a perfectly random private key over the elliptic curve. What key manager does actually is that it replaces the default PRNG used by OpenSSL, and it replaces it by a custom, I will say, PRNG, and this PRNG is initialized or seeded with a deterministic seed. So of course it will have a deterministic output, and thus we will produce a deterministic key. The deterministic seed is actually the output of the command derive kx. So we have this complex key scheduling function that will actually generate 3 private key over the elliptic curve. However, only the first one will be used by key manager. So we have a good understanding of all the key derivation steps, and hopefully what we want to do is to perform an offline generation of this key that is without the need of relying on the iLO5 hardware. So we did a complete reimplementation in C to be quite close to what is actually implemented in the original firmware based on our static analysis. We extracted again the hardware registers value using again the one-day format string vulnerability, and combining all of that, it was a complete failure. We failed to decrypt the userland image. So we needed to have more information, we needed to escalate our analysis, and possibly to interface with the cryptoprocessor to understand and validate step by step all the various stages of the key scheduling function and key derivation. So we want to talk to the cryptoprocessor because we need to interface directly with it. To do that, what we observe, what we reverse engineering, is that there is an interface made of, again, mapped hardware registers that are mapped inside the virtual memory of the task. So we will describe a bit the interface with the cryptoprocessor. So at offset 0, you have a register that we have named control flags. One can place specific flags to control the various operations of the cryptoprocessor. For example, if you want to start the computation of a digest, to add more data, to end the computation, or to reset the output buffer. At offset 0x10, we have a register that we have named offset. It is actually automatically, in hardware, incremented as soon as you write some data inside the input buffer. And it contains the size of the input data in bits. At offset 0x40, we have the output buffer. And at offset 0x80, we have the input buffer. So, to interface with the cryptoprocessor, we only need to read and write to the task virtual memory. We can do that with the one-day format string vulnerability, and we will use this primitive to interface with the cryptoprocessor. We started doing so, and quite quickly we discovered some unexpected bugs in the use of the interface by key manager. The first one of these bugs is related to the flag that we have named SHA-384 digest more data. Its semantics is quite close to an update flag. Basically, the expected behavior is that when you position this flag, the internal state of the cryptoprocessor, the internal state of the digest, will be updated with the current content of the input buffer. However, what we observed is that if the input buffer has not been fully filled, then the data are discarded or ignored. So, to give you an example, we start an operation on the Cryptoprocessor. So we write the boot hash buffer in the input buffer. We place the flag update. Then we write a new buffer in the input buffer. We write the hardware key buffer, and we place the data end flags. What we would have expected is that the final digest is the concatenation, the actual digest of the concatenation of boot hash with hardware key. However, what we observed is that boot hash buffer is actually discarded, and the Cryptoprocessor would simply wrap over the hardware key buffer. So we have a very different digest, of course, than what we would have expected. What it means in practice, if you remember what we said regarding the derivation of the initial seed, there are two inputs, boot hash and hardware key, and in practice, actually, boot hash buffer is discarded due to this bug in the interface with the Cryptoprocessor. The second bug we observed is related to non-contiguous write in the input buffer. Like we said again, regarding the offset registers, it is automatically incremented in hardware with the number of bits that is written in the input buffer. However, it is incremented without any consideration for the position of the write in the input buffer. That's really important. And however, again, internally in hardware, the value of the offset registers is used by the Cryptoprocessor to read the data linearly or contiguously. So that means that if you write a first buffer, leaves a small gap, then write a new buffer, then when you compute the digest of these two buffers, you will have a result that is different than what could have been expected. Not all the data will be taken into consideration in the digest. So we adapted our code to reflect these two bugs we discovered, and it was actually a new total epic failure because the key we computed was still invalid.
So now what we wanted to do was to find some debug information to understand where we failed in our implementation. So while debugging the key manager task, we saw that there were some debug messages present. For example, there's an intermediary state in an early stage of the key derivation, which is outputted on the standard output after being base 64 encoded. And also the final computed public key is displayed also on the standard output. So we know that the standard output is in fact printed on the UART output of the server. So we started probing some pins on the server motherboard to find the UART, and we finally found it. So when we booted the server, we can now see that these debug messages. So what we did was, in our implementation, we re-implemented the base 64 encoding of this intermediary state, and we saw that the two values were totally different. So it means that we have a failure very early in the derivation process, which is a good news. So here is where the failure should be. So there's the initial derivation seed as well as an early step in the final key derivation. So now we had a new theory, which was that the values of the hardware registers may have changed between firmware versions 1.x and 2.x. So we need better debugging capabilities to be able to read these values on a 2.x firmware. So we wanted to use some hardware debugging. So we wanted to find a debug port on the motherboard and be able to use it to read these hardware registers values. When we looked at the photographies of the HPE microserver Gen 10 motherboard on HPE website, we saw there was a port labeled as iLO debug. It's a Mictor port, which is well known in the ARM world, and it should allow us to do some JTAG debugging. So we started soldering wires to be able to interface with this port, but finally we bought a correct adapter. In the end, we were able to enumerate the JTAG chain. So we saw there were 2 processors on the chain, but we had some problem with the JTAG input, the TDI pin, and we didn't find a solution to fix it. So we gave up. We are software guys, so we wanted to find a software solution to be able to do the same. So what we did was looking for a new vulnerability in firmware versions 2.x to be able to read the SOC registers values. So our target are 2.x firmwares. We had a look at a specific attack surface we already know, which is the chief interface. This is an interface to perform communication between the host operating system and the iLO system. So from there, several tasks running on iLO are reachable from the host operating system. And one of them is the black box task. And it's really interesting because this task is also present in the recovery image, which is unencrypted. So we can open it in IDA and start studying it. So the black box task handles many commands, and one of these commands, command 5, is a kind of debug menu in expecting some commands in text mode, just like if we were in a terminal. And when it handles a command, it will output the results on the UART. For example, there's a bbfdump command taking a file as argument, and it will xdump the file on the UART. When we started looking at the handler of this command, it was like in the 19th, so there were buffer overflows everywhere, massive usage of dangerous functions such as sprintf, string copy, without verifying the destination buffer size. As a reminder, on iLO5 there are no modern mitigations, so no NX, no ASLR, no stack cookies. So exploiting this kind of vulnerability is kind of easy. So we targeted one of these command handler, which is the fview command. It will perform an sprintf on a fixed size stack buffer without checking the size. So how did we exploit it? We first wrote a small shellcode, a trampoline shellcode in the data section of the task using another command, which is chdir. And this shellcode was simply grabbing the current stack pointer value and then jumping back into the stack where our final shellcode lies. So we could, in fact, put an arbitrary side shellcode in the stack and jump to it. A little digression here. While exploiting this vulnerability, we also implemented the recovery of usernames and clear text password on iLO, which will be useful in red teams. So back to our business. Using the vulnerability, we were able to read again the hardware register values, and all the values we read were exactly the same as in older firmwares. So what we did next was directly ripping code from key manager. So we splitted the code in 2 blocks, and we executed it through the vulnerability, and finally we dumped the Cryptoprocessor output buffer to compare the values with our implementation. And values were exactly the same. So now we had a new theory, which was that our execution context when exploiting the vulnerability was in fact different from the key manager context. So we now have to kind of instrument key manager to understand where we failed. To do so, we in fact reused our secure boot bypass we found earlier. So the goal was to create a modified firmwares and add some hooks to understand our mistakes. The secure boot bypass in fact allows us to load a modified userland image using an older vulnerable boot chain, so including the bootloaders and an older kernel. So the plan was to load a modified key manager with an old vulnerable kernel. So when we first built this firmware, we used an unmodified key manager, and the iLO5 booted and displayed the same key schedule validation as in a normal boot, which is very good. And if we apply some minor modifications to the task, for example modifying a string, it will still boot. So we are now able to modify the task to understand where we failed. How can we flash an arbitrary firmware on iLO? We have two solutions: either with a vulnerability in the firmware, but it will need us to reflash a valid firmware each time we wanted to flash a modified one, either through hardware. In fact, we can directly interface with the SPI flash and write our firmware. So that's what we did. It was easier and faster for us. About the hook, we in fact just put a simple printf in the middle of the derivation scheme. So our hook was placed just after the derivation seed was computed and just before the first stage of the key schedule, key scheduling algorithm, and we dumped the derivation seed value encoded in byte 64 on the UART. So when we booted the server, we get this string on the UART. So we were able to compare it to our implementation. And when we performed the comparison, we saw that only 4 bytes were changing, which is very weird because this value is supposed to be a SHA-384 hash, and when only a few bytes change in a hash, there's something really weird. So we looked closer at the key manager code, and we saw that in fact when computing the final digest, there were no use of synchronization mechanism between iLO and its cryptoprocessor, which means that the copy loop starts before the cryptoprocessor ends its hash computing. So it starts copying some values from an intermediary state. We could check this theory by using a SHA implementation in Python and by adding a print of the intermediary state just before the final digest. And we can see that the first 4 bytes of the intermediary state are the bytes we found in the buffer we dumped. So we got our final bug, and then we implemented it in our decryption tool, and then it worked. So now we are able to decrypt the first envelope of the firmware, but also the userland image. Then we analyzed quickly this userland image. There were 4 new tasks and only a few differences, so we were like, all that for this? But anyway, the tool is now available on our GitHub repository, and the community could start using it to check new iLO versions.
Yeah, so we spent so much time understanding this last bug that we are still quite happy and very happy to restore a balance to the force. And more seriously, we really believe that our works, Nicolaio's work and the works of many others, have helped to increase the security level and awareness about iLO5 systems. So that's why the firmware analysis capability is really important for the community. Regarding the firmware encryption itself, it has, in our opinion, an unclear added value for the end users because, as we showed here, attackers are able to extract the keys exactly like we did. The implementation is particularly complex, we find, for something that is that should be much more simpler. There is no use of a real secure element, and the buggy usage of the cryptoprocessor, we can only make the hypothesis that the exact same bugs have been re-implemented in the HPE firmware production pipeline. Now, if we speak more about the iLO5 system and in itself, we find again the same interesting weaknesses. First of all, the OS primitives are too permissive, exactly like the one we abused for regarding the memory mapping. The secure boot is broken. We reused our exploit from 2018 to build a Frankenstein firmware which was perfectly functional to gain debug capabilities on the systems. And also, the complete lack of modern mitigation techniques make it simple by exploiting a single vulnerability to perform a complete takeover of the iLO5 systems. We'd like to remind you that iLO5 systems are really critical systems, so please keep them up to date, make sure they are not exposed too much, isolate as much as possible, and please monitor them. Regarding the new vulnerabilities that we have talked about within this briefing, there is an available fix by HPE which has been released in March 2021, and you can have more information in the security bulletin that is rated as critical. So before we close this talk, we would like to thank Mark Mankus and all the HPE PSRT for their reactivity. We would like also to thank our teams at Synactive and Airbus for their very valuable feedbacks during this research. Nikolaios as well for presenting his work and publishing its tools. Raphael and Xavier for the help with the server initially video. So thank you very much for attending this briefing. We'll be very happy to join you for the Q&A session. Thank you for your attention.